thermonuclear fusion. Energy for the next century. The temperature within stars, such as our Sun, is very high. Electrons separate from the atomic nucleus and form ionized matter, which overall is electrically neutral. Matter in this state is called a plasma. This constitutes the dominant state of our universe. Films of the solar surface and solar flares show these immense jets of ionized matter. These jets shoot out enormous quantities of energy, produced by a continuous nuclear fusion process inside the Sun. Thermonuclear fusion thus produces solar radiation, which is the source of all conventional energy on Earth, since it is the ultimate origin of our fossil fuel reserves. In 1951, the first heavy hydrogen bomb showed that man is able to create, in a non-controllable and explosive way, an artificial sun which attains temperatures of greater than 100 million degrees. These bombs released enormous amounts of energy by fusion. Deuterium exists in nearly unlimited amounts in the oceans. For this reason, thermonuclear fusion is one focus of our troubled search for a long-term ideal energy source. Since the first H-bomb explosion, the ultimate goal of fusion research in the world has been to harness this energy to make a continuous and controlled source of power. Let us now examine some principles. In the atoms of all elements, the negatively charged particles, electrons, describe orbits about the positively charged central nucleus. Atoms are practically empty space, since the diameter of the electron orbits is 100,000 times that of the nucleus. The nucleus itself is composed of positive charges called protons, in the same number as the electrons, such that the whole atom is electrically neutral. The nucleus contains other particles as well, neutrons. They have the same mass as the protons but carry no charge. The protons and neutrons which constitute the nucleus are called nucleons. The number of protons in the nucleus determines the atomic number Z, and the total number of nucleons, that is the sum of neutrons and protons, defines the atomic mass A. Within the nucleus, the positively charged protons repel one another, but the nucleus is maintained intact because of strong non-electrical binding forces which counteract the electric repulsive forces. The lightest atom is hydrogen. Its atom consists of one single proton around which an electron orbits. Another form of hydrogen exists called deuterium, or heavy hydrogen. Its atom is similarly composed of a proton and an electron, but in its nucleus a neutron is present as well as the proton. This atom is twice as heavy as hydrogen. There is another form of hydrogen heavier still. This is tritium, which has two neutrons in its nucleus. From the chemical point of view, all three atoms, hydrogen, deuterium, and tritium, are identical and have the same atomic number since they all contain one positive nuclear charge. But they have different atomic masses and are known as hydrogen isotopes. Let's forget the electrons for a moment and concentrate on the nucleus. Let's consider the nucleus of the element helium. In its common form, it contains 2 protons and 2 neutrons, thus yielding an atomic weight of 4. But an isotope with only 1 neutron, with atomic weight 3, exists. Next in order, we find lithium, a light metal having 3 protons normally, but with an isotope which has 3 neutrons in addition in its nucleus. If the masses of the proton and neutron are P and N, the total nuclear mass of deuterium and of helium-4, and in general all nuclei, is always less than the sum of its nucleonic constituents. This difference, M, is called the mass defect. Now, if we fuse an ensemble of nucleons to form a nucleus, a certain amount of mass will disappear. What happens to it? It appears in the form of energy, as predicted by Einstein's equivalence of mass and energy, E equals mc squared. Thus, the mass defect expresses energy liberated. The value of this energy is also a measure of the stability of the nucleus, since this is also the energy needed to separate again the nucleus into its constituents. Let's examine the problem in terms of energy. Consider 2 nuclei separated by a distance d. The positive charges Z1 and Z2 of their protons repel one another. According to Coulomb's law, charges of the same sign repel each other inversely as the square of their separation, so that F equals Z1 Z2 over d squared. As the separation decreases, their potential energy increases due to the work performed against the repulsive forces. Suddenly the nuclei fuse. The potential energy then falls to a relatively large negative value, since other attractive short-range nuclear forces enter into play. This negative value of potential represents the work done by the nuclear forces. It is the equivalent in energy of the loss of mass that we had observed earlier. All this takes place as if the nucleons are trapped in a deep well of potential energy. The potential energy of each nucleon is a measure of the nuclear stability and varies from one element to another. Helium-4, for example, is more stable than helium-3. This is also the case with carbon-12 and oxygen-16. This diagram represents the potential energy per nucleon for all the principal elements. Uranium-235 contains 143 neutrons and 92 protons in its nucleus. This nuclear structure is at the limit of its stability. One more neutron breaks it up. A reaction called fission is thus produced. The additional neutron dissociates the heavy nucleus, creating 2 lighter nuclei and 3 neutrons, which in turn break up into other heavy nuclei. Let's examine the inverse process, fusion of light nuclei. Placing fusion reactions on the same diagram, potential energy versus atomic mass, we see the inverse processes, fusion and fission, are at the extremities of the graph. We saw that when 2 nuclei approach, their positive charges repel with a force F equals Z1 Z2 over d squared. In the case of hydrogen isotopes containing 1 proton, the repulsion force is minimal, since Z1 equals Z2 equals 1. In spite of this, the electric repulsive force becomes intense as the nuclei approach, until the short-range attractive forces carried by the nucleons dominate and fusion occurs. Consequently, in order to fuse a group of light nuclei, they must receive sufficient energy to overcome the potential energy barrier. illustrate the most probable case. The fusion of two deuterium nuclei yields a helium-3 nucleus plus a neutron and also kinetic energy. Or another tritium nucleus and a proton with kinetic energy. There is another reaction even more interesting. The fusion of tritium and deuterium nuclei, which yields a helium-4 nucleus and a neutron carrying respectively 20% and 80% of the released energy. The energy liberated in this reaction is larger still. In all these fusion reactions, the numbers of protons and neutrons are conserved as in chemical reactions, but the amount of energy released in a fusion reaction is incredibly larger. Imagine the interaction of two deuteron beams aimed at each other with sufficient energy to overcome the potential energy barrier. For each fusion, there are thousands of scatterings. The physicist Lawson was the first to determine the condition which releases more energy than is consumed. He calculated the number n of ions per cubic centimeter, the interaction time τ, and their kinetic energy at a thermal temperature T, such that the energy liberated by the fusion reactions exceeds the energy consumed. These conditions on the three parameters are called the Lawson's criteria. The n τ required by the Lawson's criteria is smaller when the fuel is a mixture of 50% deuterium and 50% tritium than in the case of pure deuterium. Various approaches to satisfy Lawson's criteria may be imagined. One can employ plasma of densities higher than that of a solid, in a billionth of a second. This is fast fusion, which might be realized with laser beams. One can also use a medium of lower density, say 10 to the 14th ions per cubic centimeter, if the ions remain for a second. This is slow fusion. It supposes that the medium is isolated from the walls. One system which avoids scattering of the nuclei and contains the ions in a finite volume uses a magnetic field to confine the trajectories. We now examine its effect on charged particles. A positive ion, moving perpendicular to a magnetic field, describes a circular path around the force lines. If it moves obliquely, it has components of velocity along and perpendicular to the field, and its motion becomes a helix. An electron behaves in the same fashion, but turns in the opposite direction. Thus, ionized particles move as if they were tied to the magnetic force. Forget for a moment the parallel component and consider our positive ion's circular motion about the field. Since it represents a current, it will produce its own field which modifies the principal field. The resulting field, represented here in a plane, will be smaller inside the orbit and larger outside. The large number of particles augments this effect. The inside field tends to diminish, the exterior to intensify. The plasma has a tendency to expel the magnetic field and isolate itself from the vacuum wall by the pressure of the magnetic lines of force. It's also necessary to account for the component of motion along the field. In a uniform magnetic field, there is no restriction of motion along the field lines, and the particle can be lost. Two methods exist to overcome this loss problem. One consists of increasing the magnetic